I thought I'd cover this last section kind of briefly with some of the images from the book and then a couple of problems from the end of the chapter. I thought that the section 4.7, which kind of gets into what they call the meaning of entropy, reverts back to discussing statistics, which we did at the earlier part of the chapter. I thought it was worth going over because it has some important implications. So here's where we talk about dice a little bit. Let me, for example, sketch up here. I'm not that experienced with dice. I don't know exactly how the dots are arranged, but I think I've got a pretty close approximation here. If I had a single die that I threw on the table, there would be a 1 in 6 chance of getting any of the numbers. They would all have an equal chance. If you have 2 die, the distribution becomes more interesting to look at, though, because the combinations of the 2 die have to be added to each other, and what you find is that there end up being 6 different ways of rolling the number 7, but only a single way of rolling 2 or a single way of rolling 12. Notice how the author drew these values or the number of ways. We use the letter W here. If you think that's an accident, it's not. I wanted you to think about microstates. But in the system of 2 dice, throwing a 7 ends up being the most common result. I shouldn't say the most common result. It's the most probable result because there's 6 different ways of getting a 7. What's really interesting is when you start increasing the number of systems, then the microstates goes up really high and something really interesting comes out. So let's say, for example, there were 4 die, and I'm taking this from the text. There are a range of results if you throw 4 die, with the smallest value being a 4 and the largest value being a 24, if basically you rolled 4 6s. And let's see if I can fit this on here. Barely. Whoops, 24. And out of the much larger number of possibilities, it turns out that there are 1,296 different possibilities of throwing 4 dice. Now, not in the net number, what the results come out of each die separately. And it turns out the most common, or most probable, I said most common again, the most probable result is a total of 14. And there are 146 ways of rolling a 14. And essentially, when you do a bar graph that looks similar to the one that I just did for 2 die, you start to see a steepness in the curve that wasn't there. So look at the extension here. With just a single die, every possibility was equal. With 2 die, we kind of had this linear relationship, and then gradually you kind of get this curve. Well, as you go toward Avogadro's number, what our text tells us is that you essentially get a distribution that looks pretty close to a straight line. Let me use their words here. They say, as the number of dice increases further, we find that the number of microstates corresponding to the most probable macrostate increases rapidly. When the number of dice approaches Avogadro's number, the most probable macrostate will have such an overwhelming number of microstates compared to all the other macrostates that we will always hit that number whenever we throw that many dice. So let me translate a little bit here. What he's saying is a macrostate is the total of adding the 2 die together. Each individual microstate is the way that you get that macrostate. And for Avogadro's number, essentially we're saying that the most common value is so overwhelmingly probable that is essentially the only answer, which is just a kind of mind-blowing statistical outcome of this exercise. Essentially, the take-home message here is that that's why when you have such huge numbers of molecules, we can make these macroscopic measurements and be certain that that value isn't suddenly going to change because a bunch of the molecules are just going to head in one direction rather than the other. The numbers of molecules are so overwhelming that, and the most probable event so far exceeds something weird happening, that that's why we see what we see. Another manifestation of the way that we see statistics impacting on probability, and this is where you would, I'm giving you like maybe the first day of class of a entropy class if you were going on into grad school, but it impacts the way that energy is distributed among different possibilities in a quantum state. Now you recall, for example, that because atoms and electrons in atoms can only exist at certain levels, and you need to have discrete quantum jumps. I think in everyday language we use quantum like it's a big jump. It's actually a small jump, but the point is that there's a gap. There are different ways, and there's that W word again, that the energy can be distributed in a system of a molecule or an atom. Now this image is of a just sort of an imaginary system, but the idea is that if you had 3 units of energy and you wanted to kind of do a statistical analysis of figuring out where is the energy likely to be stored in the molecule, there's a process in statistics that allows us to calculate the number of microstates that correspond to a certain arrangement. And so this will lead to some, I don't even know what type of math this is. I don't know if it is considered statistics or some kind of number theory. But the idea here is that for the state of, let me change my color here, for the state of having all 3 atoms at the same energetic state, you would take in the numerator the number of, is that the number of units? The number of basically atoms in this case, factorial. So 3 factorial divided by the, oops, not sure what happened there. So the numerator, the n factorial, that's the number of molecules. And then you're dividing by a product of the populations of each of the individual states. So in the 0th level, this lowest level, that's 0 factorial. 0 factorial, by the way, is equal to 1. Then it's 3 factorial because that's the population of the 2nd level, which is here is labeled 1. And then the 3rd label is a 0. There's nothing in there, and it basically would go all the way up. But the point is, in this system, there's 1 microstate in which all 3 of the molecules are at the same first energy level. For the second array or assembly, I'm not sure the proper language here, the numerator again is 3 factorial. By the way, 3 factorial, if you've never seen that before, means 1 times 2 times, 1 times 2 times 3, which would end up being 6. So it's 3 factorial over, in this case now, there's 1 molecule in the ground state there, another molecule in the first excited, and another molecule in the second excited. So this is 6 divided by 1. There are 6 different ways of assembling the molecules in that arrangement. And you could see by looking at the lowercase letters A, B, and C how they can be arranged in that way to give a unique microstate. But the macro state of 1, 1, 1 stays the same. And then finally, we've got 3 factorial over 2 factorial, 0 factorial, 1 factorial. So that ends up being 6 divided by, it can't be 4, 6 divided by 2 is equal to 3. And you can see there's 3 different ways there. The point of this is that as the numbers increase, what you end up finding is the most probable result far exceeds the populations of the less likely results. And these simple examples show you how that trend begins to happen. A few problems at the end of the base part of Chapter 4. There's some additional problems that I haven't looked at yet, but we'll probably look at those during the week. So the question says, delta H of formation values in Appendix B can be positive, they can be negative, or they can be 0. But absolute entropy values are only positive. Why is that? Well, delta HF values are based on the arbitrary standard that formation reaction of elements are 0, and formation of other elements are related to that. All other reactions are compared to that standard. Absolute entropy values, that's the S bar naught values, are related to Boltzmann's ideas about microstates with the equation that's we wrote there that's on his tombstone. Since the number of microstates can never be negative, S can't be negative. There's no way to arrange that equation for a value of W to give a negative value of S. So that's why absolute entropy values are always positive. If you agree with the third law of thermodynamics, which defines zero disorder at 0 degrees K, any other state is going to have more disorder than that. Assuming you're at 298 for most of these, except the last one, choose the substance with the larger absolute molar entropy. Here we circle the H2O in the gas phase because gases are more disordered than liquids. I circled calcium chloride because it's inherently a more complex system. If I have 1 mole of each salt, the one with more atoms is inherently more complex. This one's a little tricky maybe. If you have a mole of nitrogen gas at 1/10 of an atmosphere versus nitrogen gas at 1 atmosphere, the 1 mole of gas at the lower pressure occupies a larger volume, and therefore you have more microstates. Carbon in the diamond phase is more ordered than carbon in the graphite phase. You could think of it as sp3 versus sp2. There's more sort of wiggle room, if you will, as you warm up graphite in between the layers rather than the carbons kind of locked into their tetrahedral arrangements. If you have a mole of ozone that's more disordered than a mole of oxygen gas, triatomic is inherently more complex than a diatomic. This one I thought was tricky. If I have a mole of ethanol and a mole of ether, they're the same molar mass, but the ethanol can form H bonds because we're at 298, we're in the liquid phase, which leads to a more ordered system. A mole of N2O4 versus 2 moles of NO2. Now it's true the N2O4 is a more complex molecule, but having 2 moles of particles compared to 1 is more important. And then finally, if you have let's say I have a mole of iron at room temperature and I warm it up 100 degrees. At the higher temperature, there's more thermal motion, so therefore there's more disorder. These 3 kind of run together, and I put a video into Sakai that I found online about residual entropy. I don't consider it something worth thinking too much about, but I'll explain it in the context of this question, and I'm happy to answer more questions if you have. Explain the discrepancy between third law entropy and calculated values from statistical thermodynamics. All right, so let's decipher this question. Let's go back to earlier in the chapter. What do we mean by third law entropy? Those are related to experiments. Remember how I had that multi-step process of finding an absolute entropy? Like you use that Debye approximation down close to 0 Kelvin, and I say the calculated values are always larger than what is determined using methods outlined earlier, where you have heat capacities and delta H's of fusion or delta H's of vaporization. Third law of values, if you do it the way that we did it in the book and you did it in on my earlier lectures, you actually miss some entropy sometimes due to a disorder based on differing orientations at the molecular level. Essentially, there's no way for the solid to attain perfect crystalline form if there's essentially no difference energetically in orientation. They talk about the example of carbon dioxide. Now, carbon dioxide, perhaps surprisingly, but it's complex because there's sigma and pi bonding, has a very, very small dipole moment. What this means is if you froze carbon, did I say dioxide? Carbon monoxide. If you froze carbon monoxide, they wouldn't line up necessarily perfectly in the order of them all heading the same way or alternating. They're essentially indistinguishable from each other. And so there's sort of a natural disorder that's going to happen, even though you won't be able to measure for it in the experimental ways we talked about. In calculated values, using something called statistical mechanics, you can't account for it. The equations aren't hard. To calculate residual entropy, simply insert the number of different equivalent orientations, W, in that equation, that sort of Boltzmann-like equation. In other words, since CO can either be written with C on the left or O on the left, there's two ways to write it. So when you put it into the equation, there's sort of 5.8 joules per Kelvin of entropy you can't account for by doing the standard experimental methods. This is kind of a strange area where experiment actually sort of clearly misses something. There's also a discussion about deuterated methane. You've got 4 different places for the deuterium to be, and so there's some inherent residual entropy there. Watch the video that I attached and see if it makes some sense. Again, I don't consider it a major topic, but very precise work does need to include it. Explain why the absolute entropy of graphite is greater than the absolute entropy of diamond. Is this true at 0 Kelvin? Well, you expect them to be different. I kind of mentioned a little bit earlier. Well, first of all, yeah, the graphite is going to have more disorder at room temperature, let's say, because there's more flexibility, let's say, with respect to an individual carbon atom, kind of bouncing up and down a little bit in the sheet that it's in. But if you went down to absolute 0, you would expect them to both have 0 K as long as it was a perfect crystalline arrangement. So that's about what I have on that. I will see you on Tuesday. Hope everything's going well.